Welcome back to module 5. We have discussed transverse electromagnetic mode, and transverse electromagnetic mode, one can visualize this mode if I have a laser beam propagating along this direction, and if I place a piece of paper, then I'll be able to see on the piece of paper, I'll be able to see the transverse electromagnetic mode. And we have already pointed out that rays are idealized or oversimplified model of the laser beam. In reality, a laser emits a beam of finite width or diameter. If a piece of paper is placed on the laser beam, we get the cross-sectional area illuminated by the laser beam as shown here. What we observe is called transverse electromagnetic mode of the laser. When transverse electromagnetic mode or transverse electric field intensity of the laser beam can be expressed by Gaussian function, the one we have shown here. So let's say this is the laser beam which we are seeing, and if we take the cross section of this region, and if we plot this cross section, this x versus this intensity versus I, then the maximum is I naught. Maximum is at this point, which is I naught, and it will decay following a Gaussian decay. As the energy of a Gaussian beam spreads from minus infinity to plus infinity, theoretically, it is a question, how do we define the beam diameter? If the energy spreads from minus infinity to plus infinity, how do we define the beam diameter? In many laser-based experiments, determining fluence, which is nothing but the energy by cross-sectional area, that is, we express joule per centimeter square, millijoule per square centimeter, something like that. In many laser-based experiments, determining fluence, which is defined as energy per cross-sectional area and which depends on the size of the laser beam, becomes important, and that's why we need to know how to define the diameter. We have seen that the intensity of TEM00 solution of the paraxial wave equation, which features Gaussian beam, can be written as I is nothing but a spatial Gaussian profile, e to the power minus 2 x square plus y square divided by w square. The beam waist, this w naught, we have already seen, this one is the beam waist, which is the narrowest size of the beam. Size of the beam is defined as the radius. It is not the diameter, it is the radius. Gaussian beam spot size is represented by this radius. But how do I define this radius? That's the question, because Gaussian beam, if we take this cross-sectional area, then it is the profile would be extending from minus infinity to plus infinity. Middle one is I naught. So at this point, intensity is I naught, but intensity is decaying. So question is, what point in space will define that this is my radius? That's the question we are going to address in this lecture. Size of the beam at any point as a function of z is given by this equation, which means the size of the beam will depend on the where we are measuring, the z axis. And here in this expression we have seen previously that z naught is nothing but Rayleigh length. Rayleigh length is the distance along the propagation direction of a beam from the west to the place where the area of the cross section is doubled. So this is something which we have already gone over. We have understood this general feature of the Gaussian beam already. So now we'll take a closer look at the beam waist and its meaning. What we have drawn here is that this is a profile we have drawn. The meaning of this profile I haven't discussed yet. We said that at this point, this is R, and we can express this cross-sectional area, this intensity variation in this cross-sectional area as a function of R or X, one can say X also, and this cross-sectional area is following an Gaussian intensity profile, spatial profile. This is I naught is the maximum intensity. This is intensity at this point is I naught. So one can express this this profile, cross-sectional profile, as I naught e to the power minus a r square. And we said that there is a definition of beam waste, which is nothing but this radius, this radius, this is omega naught, and omega naught is nothing but the radius of the narrowest spot in the laser beam. But at the same time, one can define it is at beam waste W naught, energy or intensity of a Gaussian beam drops to I max by E square. So 1 by E square times I maximum value when I get, that is the point I consider it to be omega naught. That's why, although we haven't defined this profile, what does it mean by this line? This line is nothing but 1 by E square intensity radius profile. So I can write down that I naught by E square, this happens when I have e to the power minus a omega naught square, r equals omega naught. So I can write down e to the power minus 2 equals e to the power minus a omega naught square. So a equals 2 by omega naught square, and according to this definition I can write down I as I naught e to the power minus 2 r square divided by omega naught square. So this is the intensity profile expressed in terms of omega naught. And what is omega naught? It is the radius of the narrowest spot, which is defined by the point where the intensity drops to the intensity drops to 1 by E square times I max. So let's say this is the point where intensity is I naught by E square. This point is called omega naught. That's the way we give the definition. And in general, as omega will change, in general we can also write down 2 r square by omega square, where omega is the size of the beam, which will depend on beam waste, narrowest size, multiplied by 1 plus z by z naught square. Z naught is the Rayleigh length. So this is the definition. So whenever we show the Gaussian profile like this, we this profile indicates that we are drawing 1 by a square intensity radius profile. For many laser applications, including ultrafast spectroscopy, measuring beam width becomes important for the laser output characterization, because generally we express the fluence as energy per cross-sectional area, and this cross-sectional area depends on how we are defining the width. Let's say this is my width, and I can express this width as the beam waist W naught. So question is, how do I get the W value at different point of the laser beam? A technique called the knife edge method is widely used for measuring the laser beam width. Its main advantage is the simplicity and possibility to use for wide range of radiation wavelengths and powers. The measurement principle is depicted here. The beam is progressively blocked by a knife edge. We take a knife edge, this is called knife edge. We can use a razor blade for the knife edge, and we progressively block the beam. We scan it along the x-axis, and this is the power meter. We measure the power as we block the beam by a knife edge, and the transmitted power is measured as a function of position across the beam, as a function of x, as shown here. Therefore, in the position where the beam is not blocked by the knife edge, the maximum power is measured. On the other hand, the measured power is minimum, typically 0, when the blade covers the whole beam. In this experimental setup, the knife edge measurement setup, we use a translational stage. So this knife edge is translated along the x-axis, and we at different position we measure the power which is not blocked. Now this is the way we get the knife edge measurement, and if we measure it, then experimentally what we see a typical profile something like this. This point is x naught, this is the x, and we start with 0 because we have blocked it, or vice versa. If we don't block it, we start with maximum, then slowly, this is the I max, slowly it drops down and then goes to 0. And the typical nature of this is the power meter. We are plotting the power, unblocked power of the unblocked beam. So if we plot them, then we get this profile. This profile is equivalent to an error function, and how it is related to error function, that's exactly what we are going to discuss next. We obtain a curve similar to the one depicted in this figure. This kind of curve we obtain in this measurement as a function of x, and this is x naught, and as many laser applications we use Gaussian beam, TM00 mode we use, the power detected by the scanning edge measurement can be easily estimated from the area under a portion of the Gaussian function. So basically what is going on, I have a beam propagating along this, and a knife edge is cutting the beam and allowing the beam, this much beam at a particular position, and I am checking with the power meter. So, this cross sectional area can be expressed as a Gaussian beam spatial profile that we have already seen, and maximum is max I. So, when we are blocking the beam, we are, let us say, blocking up to this part, this shadow regime is blocked, and if the shadow regime is blocked, this middle is x naught. If the shadow regime is blocked, then what we are doing, power meter is finding, this is, let us say, x1 position. So, what power meter is doing, V signal is nothing but minus infinity to x1 integration of I naught e to the power minus a x square dx. So, this measurement estimates the area under the portion of the Gaussian beam which is not blocked yet. So, this shadow part is blocked and this part is unblocked, and with the power meter we are trying to find out the total energy, and that is why instead of taking the limit from minus infinity to plus infinity, we are taking limit from minus infinity to the x1 point. Let us assume that a knife edge blocks everything at x equals x1. So, this part is blocked, let us say. If this part is blocked, then the power meter records energy of the beam which is unblocked. This is nothing but the area of the Gaussian from minus infinity to x1, because the power detected by the power meter is directly proportional to the area under the Gaussian from minus infinity to x1. So, instead of this general form, I will use this general form which is suitable for the present work, is I equals I naught e to the power minus a x minus x naught square. So, this is representing the Gaussian profile which is centered at x naught. The area under the unblocked portion is now given by the area under the unblocked portion which is minus infinity to x1. This is given by minus infinity to x1 I naught e to the power minus a x minus x naught square dx. That is the area. I split this into two regimes, minus infinity to x naught I naught e to the power minus a x minus x naught square dx. Another regime is x naught to x1 I naught e to the power minus a x minus x naught square dx. So, these are the two regimes I have separated. I have separated these two regimes because I can make use of this regime minus infinity to x naught, that is minus infinity to the maximum. It is nothing but, because it is a symmetric function, it is nothing but, this part is nothing but half of minus infinity to plus infinity total area, that is nothing but e to the power minus a x minus x naught square dx, this part which is half I naught square root of pi by a, standard integral we are using. So, it's a, so the first part, this integral is giving me half of the total area under the curve. But next task would be to find out this area. So, question is, how do we find out this area? In order to find out this area, we have to introduce error function. To get error function, we have to consider normalized Gaussian function, because error function is related to the normalized Gaussian function. So I will first normalize our Gaussian function e to the power minus a x minus x naught square. This can be normalized. If I normalize it, then I'll integrate it minus infinity to plus infinity, and area under the curve integration is going to be 1. So this gives me directly I naught equals square root of a by pi. This is normalization constant. This is the normalization constant. Okay, so a normalized Gaussian function of the form which we have taken can be written as a by pi e to the power minus a x minus x naught whole square. This error function is obtained when we integrate normalized Gaussian function from minus x1 to plus x1. So I have to now integrate this normalized Gaussian function minus x1 to x1 square root of a by pi e to the power minus a x minus x naught whole square dx, which is nothing but 2 multiplied by 0 to x1, because it's a symmetric function, so twice the half of this function, which is nothing but a x minus x naught whole square dx. Or we can write down as square root of a by pi 0 to x1. So this function is called error function. So this error function of x1, limit is going to be up to x1, is nothing but 2 square root of a by pi 0 to x1 e to the power minus a x minus x naught whole square dx. This is error function. And if this is error function, then I can write down this integral 0 to x1 e to the power minus a x minus x naught whole square dx is nothing but half square root of pi by a error function of x1. So I can now, given this fact, and how does it look like, I'll show you how does it look like. So finally we get the area which we are interested in, minus infinity to x1 is nothing but half I naught square root of pi by a plus half I naught square root of pi by a error function of x1, which is nothing but half I naught pi by a 1 plus error function of x1. So I have a Gaussian spatial profile like this, which is centered at x naught, and I am now plotting up as a function of x1. x1 can be anything. So this, if we plot x1, error function should behave like this. So this is x naught. So at this point, how do I get this point? At this point, the value of error function indicates this integration. up to x1. So integration of this. So basically this shaded regime is the blocked beam. Only beam which is unblocked is this part, and that's why you have taken integration from minus infinity to x1, and I got this point. I got this point by taking integration from minus infinity to plus infinity, sorry, minus infinity to x naught. So this regime is blocked. On the other hand, I get another point here. How do I get this point? I get this point by taking integration from minus infinity to x1. This is x1, this is x1. So this regime is blocked and this regime is unblocked. And this is the way we get this error function. And question is, how do we define? So basically in the experiment we get this error function behavior. This is the measurement we see, and once we get the measurement done, we can find out from x naught to x naught is where the maximum intensity I should have. I should the maximum of the Imax should appear. This is where Imax should appear, and so all we need to do is that we have to get from this Imax, we have to get E square by Imax point. Let's say E square by Imax point is here. At this point I have Imax divided by E square. So in the end I'll be able to define this as omega naught from the experiment. This omega naught is nothing but the narrowest size, and if it is not omega naught, then it's omega. This is the size of the beam. So with this we will take a look at the specification. In module 2 we have looked at different specification of the laser system manufactured by different vendors. We have gone over the meaning of pulse width, repetition rate, average power, pulse energy. Already we are familiar with this features of the laser system, ultrafast laser system. Now based on the present module, we can also understand two additional features of the femtosecond laser beam. This feature suggesting that what kind of mode quality we have, that is TM00 mode, which is frequently used in the laser system. But in addition to that, we are defining beam diameter as 1 by E square. So when we say that beam diameter is 10 mm, it means that it is the 1 by E square intensity radius we are talking about. So basically we have an intensity profile at a particular point, that is the X cross sectional profile, and this is the maximum I naught. We are going to take I naught by E square, and this diameter, this radius, this is the radius and this is the diameter. So we are talking about when you say 10 mm 1 by E square beam diameter, it suggests this. So with this we have come to the end of this module. Here we have discussed little more details of the TEM00 mode, how to measure the diameter of an ultrafast laser beam, and how to express it, and we see that error function is the response which we see in the knife edge measurement. We'll meet again for the next module.